today's video here is a nice problem is coming from the Hong Kong. So we get this information for all n as a positive integer satisfy these both conditions. So we get this product n plus number 1 is multiplied by 2n plus 15, and the second product, which is n, is multiplied by n plus number 5, have the same prime factors. Okay, so the goal, we are going to find the largest value of n satisfy this condition. Okay, so before we get started, I would like to remind you about the factorization prime. So the factorization prime is going to be written on this form: p equals p1 to the alpha 1, p2 to the alpha 2, all the way down to the pi to the alpha I. Okay, for example, if you have 45 equals 3 square is multiplied by 5. So this is the factor. This one is going to be written on the same form that I have here. So the first product and the second product must have exactly the same prime factors. Okay, now let's jump into this one to see what it's giving us. Let p be a prime factor of n is multiplied by n plus number 5. Okay, so n plus number 1 factor 2n plus 15. Okay, which means p divides this one as well as this one. Okay, because they are shared the prime factors. Okay, so starting with the first product, n is multiplied by n plus 5. Here n factor n plus 5 equals n squared plus 5n. Let's work on this one to get something very important here. So what to do here, I'm going to split this number 5 into two parts. I get n squared plus 4n plus n, then adding 0 by adding 4 minus 4. So now I'm going to extract the common factor. So I get n squared here, I get n. I'm going to write it as n factor n plus number 1. This number 4 factor n plus number 1. I'm taking 4n and number 4. I'm going to isolate this number 4 as a single integer. So now what to do? So we get n factor n plus number 5. Since p divides this one, so we get p divides n factor n plus number 5. This implies also p divides n, also divides n plus number 1. Why? Because p divides the left hand side of this equation, which means p must be divides the right hand side of this equation. In the other word, p must divide number 4. Since p is a prime, which means p is going to take number 2. Okay, so this is very important value that I have extracted. I'm going to use it all the time now. Now we have extracted p equals 2, which means 2 divides this one, but 2 cannot divide this one. 2 cannot divide 2n plus number 15 because this is odd. Because is odd. Thus, if number 2 cannot divide this one, which means n divides this one. Thus, 2 divides n plus number 1. Also, n must be odd. Why? Because 2 divides this one. Because 2 divides n plus number 1, which means n plus number 1 is even. In the other word, n must be odd. Okay. Also, if you take a look at it here, 2 divides n factor n plus number 5. Since n is odd, which means 2 must be divide n plus number 5. Okay. But here, since we found p equals 2, which means n plus number 1 is going to have only one prime factor, which is 2, because the only one that we get. So this one is telling us n plus number 1 equals 2 to the a. This is the prime factorization form, because since we get p equals 2, it doesn't mean we are going to take n plus number 1 equals 2, which means it's going to be a power of 2. Okay, so depends on the value of a. Okay, but we don't know about n plus number 5. N plus number 5, we know just 2 divides n plus number 5. We need to work more in order to check how n plus number 5 is going to be. So which means we know n plus number 5 equals 2 to the b is multiplied by something. This something we don't know about it. We need to check the other product, this one. Work. Notice here, if you look at this product, we know GCD of n and n plus number 5 is going to be number 1 or 5, since we get number 5 here. Okay, it cannot be number 2 because we know n is odd. Okay, but we don't know which one exactly is 1 or 5. Now let's work on the other side in order to check exactly what's the GCD of these terms. Okay, we need to work on this product in order to find out what's inside of this box. Okay, now let's get rid of this one and move on to the next step. Now previously we have extracted this information. We get n plus number 1 equals the power of 2. Also we get n plus 5 equals the power of 2, but is multiplied by something else. We don't know about it yet. So what we know just GCD n plus 5 equals 1 or 5. If we knew GCD equals 5, we don't have to do the second job. We will find 5, it will be divisible by this one. Okay, so notice here this product n plus number 1 factor 2n plus 15 is going to be 2n squared plus 17n plus 15. Let's split this one in multiple terms. So this one is going to give us n squared plus 5n plus, what I'm doing to this one, because I have to transfer this one into this form, because we have a relationship between this one and this one. We get n squared plus 5n. That's what I want to do here. Okay, so plus other terms, so get n squared plus 12n, because 17n equals 5n plus 12n plus 15. Let's take n as a common factor. I get n plus 5 here. N is multiplied by n plus 5. So we get here n factor n plus 5 as well, plus 7n plus 15, because we get 5n plus 7n equals 12n. Okay, so we get a common factor here. Let's take it as a common factor. We have 2 times n is multiplied by n plus 5 plus this one. This one is going to be 7 factor n plus 5. Another common factor here is coming up. So we get 7n, which is here. We get plus 35. But we get 15 here. We need to get minus 20. Subtract minus 20. So we get n plus 5 factor 2n plus 7 minus 20. Okay. Notice here, this 20 equals 2 squared is multiplied by 5. Let's stick this one up here in order to make the equation clear. Okay, since we have this equality and we know both products are having the same prime factor, okay, which means this prime factor divides this one as well as this one, which means this prime divides this 20. Since we get a factorial prime in 20 is 2 and 5, which means you will have only 2 primes. What to do here? So we are going to skip number 2, are going directly to number 5, because we already determined n plus number 1 equals power of 2, as well as this one. We don't need number 2 here, we need number 5. Okay, so the problem, so we know n plus number of is not be divisible by number 5 because absence of number 5 here in this power, because we don't have a power of 5 in n plus number 1, which means 5 divides this one. Okay, so it is a little confusion in this one. We don't know 5 divides this one or this one. We are going to prove this one. We are going to do that by the way of contradiction. So by the way of contradiction, suppose 5 divides to n plus number 7. Okay, so this one equivalent according to the divisibility statement, which means 2n plus number 7 equals 5k. Okay, let's plug this one into here. Plug in n plus number 1 with 2 to the a factor. So we know 2n equals 5c. We know 2n equals 5k minus 7. 5k minus 7, which equals n plus 5 factor this one. This one will be replaced with 5k. So here is an issue here. Here's a problem. We know 5 divides this one. Here is a problem. 5 not divides 2 to the a, but 5 divides 5 to the k, but 5 not divides 7. Okay, which is impossible. Possible, which means this number 5 divides this term, not this one. 5 divides n plus number 5. Now let's get rid of this one and move on. Now let's keep working on this one. Now we have determined what's inside of this box, which is 5 to the c as a power of 5. Okay, now we get a nice thing here, replacing this equation into this equation. So let's replace n with 2 to the a minus number 1 plus 5, which equals 2 to the a plus 4, which equals 2 to the b, is multiplied by 5 to the c. Okay, now we have determined this nice equation. Now we need to determine a and b. For c plus, determined b. So if a is bigger or equal to 5, if b is super equal to 3, what's gonna happen here? This term at least is going to take number 8, which means 8 divides the right hand side of this equation, but 8 cannot divide the left hand side of this equation. Whatever a is, if you have a is equal to 5, let's take this example. If a equals 5, you get 32 plus 4, which is 36. 36 never ever it will be divisible by number 8. Okay, so finally b must be equals to 3. But if you're trying to take number 4, this equation satisfied this condition. B equals 2, I get here 4. This one is a multiple of 4, whatever the value of a above this point. Okay, so which means this one immediately is telling us b must be equals 2. Let's replace this value of 2 into here. So I get a new equation of 2 to the a plus 4, which equals 4 is multiplied by 5 to the c. Let's divide both sides of the equation by number 4. So I get 2 to the a minus 2 plus 1 equals 5 to the c. So we have I have a nice reduced equation here. Now we need to determine a and c. So how to do that? It's more simple. I'm going to reduce the equation to the mod 8. So we get a super equal to 5, which means a minus 2 is super equal to 3, which means I get 5 to the c is a congruent to 1 mod 8. Why? Because this one is 0. As we have a minus 2 is super equal to 3, this one it will be 0 if you reduce it to the mod 8. Okay, so this one is telling us immediately c is an even. I'm not going through the chart. It's more non-marginal, okay, because always when you get number 1, we get 5 to the c number 1, always in even integer, when you get number 1 here, you get c is an even. Now let's get rid of this one and move on to the next one. So what does this mean? If c is an even, I'm going to reduce this equation to the mod 3 as well. So we get here, you get 2 to the a minus 2, which equals 5 to the c minus number 1. If I'm going to reduce this one to mod 8, I get here. If I'm going to reduce this one to mod 3, I get minus 1 to the c minus number 1. Because 5 equals 6 minus number 1. Okay, 6 will be divisible by 3. So this one is a congruent. If c is an even, I get 0 here. 0 mod 3. Okay, c is an even. Which means 3 divides 2. Which means 3 divides 2 to the a minus 2. Which is impossible. If this one is impossible, which means this assumption is wrong. Okay, because we have built our proof on this assumption, which means a is going to take the following values in this set. You get 1, 2, 3, and 4. Now let's get rid of this one and take the largest case here. Now we don't need anything else. We need just this equation, okay, and this set. Now let's go back to the question. Find the largest value n. What's the largest value possible you can take in order to verify this condition? So to get a large value, which means you are going to take the large value of a, this one. If a equals 4, then plug in this one here. So I get n equals 2 to the 4, which is 16, minus 1, which is 15. But how we know this is the largest value of n? We are going to check it in both products and to see what the product is. Okay, first let's check it here. So we get n plus number 1 equals 15, which is 16, factor 2n plus 15, which is plus 15, which is 45. 16 is the same as 2 to the 4. 45 is the same as 3 squared is multiplied by 5. Let's check it also in the second product. So we get n plus number 5, which equals n 15. 15 plus 5, which is 20. 20 is the same as 2 squared is multiplied by 3 is multiplied by 5 squared, because you get 5 from here and 5 from here. We get only 1 3 here. Okay, so which means, as I said before, both products are sharing the common prime factor. Okay, we get number 2 here, but we skipped number 3 if you remember, because we didn't need that, because what we need just the largest value of n. We were able to find out by using this equation and the second equation, which is n plus 5. Okay, so this is the largest value satisfied this condition. So I have done this problem. By the way, don't forget to hit subscribe and support channel, like, comment and subscribe. Thank you for watching. I will see you next video. Bye.